Hello friends, so today we are going to discuss 4 questions, and these 4 questions are from electrostatics. So 1 second. One second. It's not working. Okay. Okay, so in the first question, we are given a spherical volume of radius r is filled with charge of uniform density rho. We want to know the potential energy U of this sphere of charge, that is work done in assembling it. So in this case, in the question itself, it is mentioned that we are going to find out the potential energy, that is our U, and that is nothing but the work done in assembling that. Okay, it means in making this sphere. So we can say in order to assemble the sphere, we are going to consider that we are going to assemble it rather shell by shell. Okay, so we are going to bring a shell from infinity to a particular point, and that will be continuously added. Ultimately, we are going to get a sphere. So in this case, we are going to assemble sphere shell by shell. And which means that we are going to build a sphere by bringing thin spherical shells from infinity. So which means that building a sphere by bringing thin spherical shell from infinity. And so based on this, so initially let us suppose this is the point where we are going to assemble a shell, the sphere, and we are bringing the shell from infinity. Okay, so this is a thin spherical shell which we are bringing to this point A, and initially there is no charge here. So ultimately, after some time, we assume that we have already assembled a sphere of radius small r, and we are going to find out what will be the potential because of this assembled sphere, and then based on this we can find out easily our this potential energy, or we can say work done. So we are going to consider that we already have already assembled a sphere of radius r, and this sphere is a uniformly charged sphere. Therefore, we can write the charge inside the radius r. Charge inside the radius r, and let us call this as charge as q, and that is dependent upon radius r. So we can write that our this charge will be equal to our density, which is nothing but our volume charge density. So this will be going as 4 by 3 pi r cube. So this is the total charge inside the radius r. And based on this, we can easily find out the potential at radius r due to this charge. So you can find out the potential at radius r due to this charge, and let us call this as V at radius r, and that will be equal to 1 upon 4 pi epsilon naught charge and divided by the radius r. And we can easily substitute this our q of r, so we get that potential at distance r will be equal to 1 upon 4 pi epsilon naught, and this q of r is our rho 4 by 3 pi r cube and multiply by 1 by r. And we can easily solve it. This pi 4 and 4 goes away, and this r goes by square. So we get this as our rho r square upon 3 epsilon naught. So this is the potential because of the charge q of r. Now we have to do the work done against this particular potential. Okay. And like I said, we are going to bring shells from infinity near this sphere. So first of all, let's find out what will be the charge on the thin shell added at radius r. Okay. And for this, let us assume that this was our original sphere r, and we bought a thin shell, and that thin shell is going to attach with this original sphere of having radius r, and we assume that this thickness of thin shell is our dr, and it is having a charge of our dq. Therefore, you can say that a shell of thickness dr carries a charge and that charge is our dq, and then dq will be equal to the charge density, and we have this as our 4 pi r square times dr. So this is the charge on this particular thin shell. Now we can find out the work done in bringing this shell. So you can say that our work done in bringing this shell, and that work done will be nothing but our potential energy. So we can write that this du will be equal to the already potential which we are having, that is V of r, and multiply by the charge on the shell. So we simply substitute their values. We have this as rho r square 3 epsilon naught, and this comes as rho 4 pi r square and dr, and we can write this as our du will be equal to 4 by 3 pi rho square r4 and dr. Now in the question it is given that we are going to make a sphere whose radius is capital R. So it means the limit of this radius small r is going to vary from 0 to capital R. So we are going to get the total energy. Therefore we can say that our u will be equal to integral from 0 to r du, and we get this as our 4 by 3 pi rho square 0 to r raised to power 4 and dr, and this gives us the total energy u will be equal to, and this will be r raised to power 5, so this comes as 4 upon 15 pi rho square r raised to power 5 divided by epsilon naught. So this is our total energy. And if you want to write, we can also write this expression in terms of charge also. So we know that our total charge which is our q is rho 4 by 3 pi r cube, and from here we can find out our rho. So rho will be equal to 3q and 4 by 3 pi r cube, and we substitute this into the equation of our energy. Therefore we get that u will be equal to, this will be 3 by 5 1 upon 4 pi epsilon naught q square upon r. So same expression, but we can write this in terms of the given charge, that is our q. Next question. So the question states that it is two parts question. First one is, consider a fixed hollow spherical shell with the radius r and a surface charge density rho sigma. A particle with mass m and charge minus q that is initially at rest falls in from infinity. What is the speed when it reaches the center of the shell? Assume that there is a tiny hole that be cut in the shell to let the charge through. So for this part A, the figure is already given to us. So this is our charge, which is our minus q, and mass is given as m. So it starts from infinity, and ultimately we have to find out what will be its velocity at the center of the shell. So this is our first part. In part B, consider two fixed hollow conical shell with base radius r, slant height L, and surface charge density as our sigma, arranged as shown in the figure. A particle with mass m and charge minus q initially at rest falls from infinity along the perpendicular bisectoral line as shown. What is its speed when it reaches the tip of the cones? So this is for our part B. Again we have a mass m charge is minus q, and it falls from infinity. And we have to find out what the velocity when it reaches this cone, okay, vertex, common vertex of both the cone. This is the basic question. And so we are going to start by finding out the potential, and that potential is going to help us to find out the energy, and that we can use the conservation of energy. So let us start with part A. And for part A, this is our hollow spherical shell. Okay. So for hollow spherical shell, we can write the total charge. So we can say total charge on a hollow spherical shell and let us, that is our q, which will be equal to 4 pi r square times the charge density. Okay. And we know for a spherical shell, the potential at infinity, ideally we can assume that it is equal to 0. So we can say for spherical shell, we can write that potential at infinity in ideal case is equal to 0, and for everywhere inside including the center is equal to the surface value. Secondly, we can say the potential everywhere inside including center equals the surface value. Therefore, we can write that potential at the center is equal to 1 upon 4 pi epsilon naught charge upon the radius r. And now we are going to use our energy conservation. Okay. And for that, okay, we are going to use our energy conservation, and the particle comes from rest at infinity, therefore we can say initial energy will be equal to 0. You can say its initial energy, that is of E of I, will be equal to 0. And final potential energy at the center final potential energy at the center, let us call this as our UF, which will be equal to minus Q multiplied by the potential at the center. And so we can write this as 1 upon 4 pi epsilon naught Q multiplied by capital Q and times R. And then we can find out the gain in kinetic energy. Okay. So you can say that kinetic energy gained will be equal to the let us suppose that is our K, and that is equal to minus delta U. Okay. And initial energy was equal to 0, and this was our final energy. Therefore, we can write it will be equal to 1 upon 4 pi epsilon naught Q, capital Q upon R. Then we can say that our speed at the center, that is our kinetic energy, is nothing but our half mv square also. Therefore, we can write that kinetic energy is our half mv square, which will be equal to 1 upon 4 pi epsilon naught Q, capital Q upon R. And we get that our this goes by 2 and rest will be same. So we get this V is equal to one upon 2 pi epsilon naught multiplied by Q, capital Q and MR and its square root. And we know that our capital Q is our 4 pi R square and charge density. So we can also substitute it. So this will be giving us 1 upon 2 pi epsilon naught Q upon MR times 4 pi R square and sigma and its square root. And here this R goes by square, pi goes by pi, 4 goes by 2, and I think that will be all. So this will be coming as our 2Q and charge density multiplied by R and M epsilon naught, and it is square root. So this was the velocity at the center of this shell. Now we come to our two charged conical cones connected at the vertex. So we have our part B, and we have to remember one key concept here, that our potential energy is only dependent upon the electric potential. Okay, it is not dependent upon the path or the shape of the surface, like we calculated also. Okay, so we simply found out that our potential energy is dependent upon the potential, not on the shape. Okay, so ultimately here also we saw that our potential energy is only dependent upon the potential. Okay. It's not dependent upon the shape. Shape means here we are discussing now part B, which is a shape of the cone. The part A, it was a sphere. Okay. The shape doesn't matter. What matters is the potential. So we have to remember this particular thing. Therefore, we can write it out. We can say that our potential energy depends only on the electric potential not on the path or shape of the surface. Or shape of surface. And second thing, specifically in this particular case, we have to remember that the electric potential at the apex of a conical surface depends only on the base radius, that is r, and it is not dependent upon the slant height, okay, specifically for this conical surface. Okay. Therefore, we can also say that the electric potential at the apex means basically vertex of a uniformly charged conical surface depends only on the base radius. In this case, that is our r, not on the slant height L. Slant height L. And in this particular case, we are having two identical coils and they are arranged symmetrically, okay, and they are joined at the apex, at the vertex. So you can say for two identical cones arranged symmetrically, the total potential at the tip, and let us call this as V tip, this will be equal to charge density radius and divided by epsilon naught. Okay. And this looks like is same as the potential at the center of a charged spherical shell. Okay. Yeah, so in this case, okay, if you substitute value of Q, this will be giving us the potential at the center. Okay, so they are same. So we can say which is okay, let's leave it. Okay, so this is same as our potential at the spherical center of the spherical shell. Okay. Once again, same law, we can use conservation. Energy conservation gives us half m v square will be equal to charge multiplied by the potential at the tip, and we substitute it, we get this as our half m v square will be equal to q multiplied by our density multiplied by r and epsilon naught. So we get the velocity will be equal to 2q sigma r and divided by mass into epsilon naught and its square root. So this is our main velocity. Okay. And this gives us come to the next question. Okay, so in this question it is given that two strips of charges as shown in figure have a width b, infinite height and negligible thickness in the direction perpendicular to the page. Their charge densities per unit area are plus minus sigma. Find the magnitude of electric field due to one of the strips at a distance x away from it in the plane of the page. Part B, find the force per unit height between the two strips. So basic figure is given to us. So we are having two strips, okay, and charge density is same but of opposite. Left one is having a plus and right one is having a minus. Okay. And let us assume that this is our origin, x is equal to 0. Okay. And so on the left side we are going to get x is equal to minus b, and on the right side we are going to get x is equal to plus b. And the total width of this entire strip will be equal to 2b. Okay. And so we are going to find out part A, find the electric field in one of the strips. Okay. In one of the strips that is distance x away from it. So we can choose any one strip and try to sort it out. Okay. So we are having part A. And for part A, we are going to consider the strip of our left side. Okay. So we consider the strip which is our left. We consider strip left side. And so let us draw the figure. Okay. And we consider a, suppose this is the x-axis and this will be our y-axis, because these strips are perpendicular to the plane, so we can consider this as y-axis, and to the left of it there is one strip and to the right of it there is another strip. So this is our x equal to 0, x equal to minus b, and this is equal to x is equal to plus b. And let us consider a small, you can say like a small, because this is our strip, so we are going to consider a small pipe-like structure, and whose thickness is our dx, and its distance away from y-axis is, let us suppose, our x prime. And it is given, or rather we can say ask in the question, that we have to find out the electric field at a distance x away from it. So let us assume that the position of this x is somewhere here, and this is our x. And therefore we can say that this distance will be equal to over x minus x prime, which we are going to assume that this is our r. Okay, so this is our point x from the and so we have to remember that, so let us write that consider a thin, what we can call it, let us consider a thin, let us call this strip only, of thickness dx. Therefore we can write that charge per unit height that is our d lambda will be equal to charge density, and let us call this as our dx prime. Therefore we can find out that the field, because of this thin strip at the point x, and that is this is our x is equal to x. Therefore we can write that field from the line charge and we know that field is suppose our dE, then this dE will be equal to, and this is our 1 upon 2 pi epsilon naught d lambda upon r, and we can simply substitute value of r, so we get this as our dE 1 upon 2 pi epsilon naught d lambda, and this is x minus x prime, and we are going to find out because of the entire strip. Therefore we can simply integrate it, so we can say for complete strip, electric field at distance at point x will be equal to, and we can substitute our this d lambda, so this will be 1 upon 2 pi epsilon naught, and this is our sigma dx prime upon x minus x prime. So we get this as integration from 0 to b, and this is dx dE. So we can get our electric field at a distance x will be equal to, this will be sigma 2 pi epsilon naught 0 to b, and this is our dx prime x minus x prime, and integration is it's quite easy, so we can simply write this will be equal to sigma 2 pi epsilon naught natural log of x upon x minus b. Okay. And now we come to a b part, and in the b part it's asked for the force per unit height between the strips. Part B, we are going to find out the force per unit height between the two strips. Okay. And so for this we are going to find out the force on the negative strip due to positive strip. Okay, because it is not mentioned in the question which strip is we are going to use for the calculation of the force. Therefore, we are going to find out the force on the negative strip due to the positive strip. And so in order to find out the force, we are first of all going to find out what will be the electric field acting on the negative strip. Okay. And so we are going to find out the field acting on the negative strip, and we are given that our positive strip, it varies from minus b and to 0. Okay. So which basically means that at a point x, and that point x if belongs to 0 comma b, the distance to a source point which is our x prime, and that belongs to minus b comma 0 is, and that distance will be equal to our x minus x prime. So based on this, we can easily find out the field from the positive strip at a distance x. Okay, in the shorter terms, we are going to find out the field from the positive strip at a distance x. You can say field from the positive strip at x is, and we can write this as our E of x is equal to, this is sigma 2 pi epsilon naught integration minus b to 0, and this comes as our dx prime upon x minus x prime. Okay. Same thing but in the opposite side now. Okay. That's why we have taken that, and it is quite easy to understand also. If we want to, we can just draw the figure also, and this is our x-axis, and we have two strips. One strip is x is equal to minus b, and we are having, this is our y-axis, and our other strip is at x is equal to b, and this is our positive and this is our negative. So in this particular case, we are going to find out the field from the positive strip at a x is, and in this case we have to remember that we are going to find out the force on the negative strip due to the positive strip. It means we are going to find out the electric field first of all because of the negative strip at a certain distance x. So for that we are going to assume that we are having a small dx prime, and the point where we are going to find out the force is at somewhere here. Okay, so this is at x. Therefore we can say that the distance between these two will be equal to over x minus x prime. And for that we can, so this is our x and this is our x prime. So we have assumed a small strip dx prime which is at a distance x prime from negative of b. Okay. And the point of interest or a strip of interest is at x is equal to x. Therefore we get this entire distance is equal to x minus x prime. So this is the basic. Okay. And because of that we can easily write that our small electric field is our dE. Same thing which we used in our part A also. So first of all we can write that what will be our dE because of this strip at x, and which we have already calculated also. Same formula we are going to use this, or we can say this formula. And so this is our small electric field because of our strip. Okay, so let me write it here. So this will be equal to 1 upon 2 pi epsilon naught, and this will be our charge density, sigma dx prime, and the distance between them, and our total electric field will be nothing, the integration of this, and integration will be minus b to 0 because our strip is varying from minus b to 0. So from here we get this result. And now it is quite easy to integrate. Therefore we can say that our electric field at x will be equal to sigma 2 pi epsilon naught, and this comes as natural log of x plus b upon x. Okay. And we are supposed to find out the force. Okay, so we found out the electric field. Now we come to the force. Okay, so the small force.
Okay, I found.
Sorry. And so you can say the force per unit height so based on this we can write for an element dx prime, or let me write it different way. So we can say that force on an element dx of the negative strip and that force is our dF, which will be equal to our charge and our electric field times dx, and we are supposed to find out a force per unit height. So you can say F upon H will be equal to charge density, and it comes integration 0 to B, and this is our Ex times dx, and this Ex electric field we have already calculated. So you can say this will be a sigma, this is our 0 to B, and natural log of x plus b upon x, and this is our dx. And if we evaluate the integral, we get this force upon height is equal to, and this integral will be giving us one second, I missed something. Yeah, I missed this part. Okay, so this will be equal to our sigma square and 2 pi epsilon naught. So we get this as our sigma square upon 2 pi epsilon naught, and okay, sigma square 2 pi epsilon naught, and this comes as b natural log of 2. Okay, so this is our force per unit height because of one strip to the another. So in this particular case, we have to remember two things. First of all, we found out what will be the electric field of because of this entire strip at this particular point. And then we are going to find out the force because of the electric field on the entire strip. So it will be using the integration part twice. Okay. And next question. So this question, it states that a sphere of radius A is filled with a positive charge with a uniform density rho. Then a smaller sphere of radius A by 2 is carved out as shown in the figure and left empty. What is the direction and the magnitude of the electric field at A and at B? Okay. So basic figure is given to us. So this is our empty part, and this is having a charge density of rho. Point A is at the circumference of a smaller radius, and radius is our A by 2. So basically this point A is at the center of this bigger sphere. Okay, let us call this as O. And the center of the smaller, let us call this as O prime. Okay. And we are going to assume that the portion with which we are moved is having a charge density of minus sigma. Okay. And, sorry, not sigma, minus sigma, but minus rho. And the outer one is our plus rho. Okay. So we are going to consider it as a outer one we are going to call as a big solid sphere, and the inner one we are going to call it a spherical cavity. So we are given that we are having a spherical big solid sphere of radius A, and A by 2 is carved out. Okay. So based on this, we can write that, let us write it, cavity center is of O prime, okay. And this big sphere center is, let us suppose it is our O. Therefore, we can write that the distance between O prime will be equal to A by 2. Okay. And please remember, this point O is overlapping with our A point. Okay. We have to remember this case. Okay. And okay, let me, so point A is having two locations simultaneously, okay, and because of the cavity it is on the surface, and because of the solid sphere it is at the center. Okay, so position of A is having two positions simultaneously. So point A is on the surface of inner cavity, and this point A is also at the center of the big sphere. Center of the big sphere. Okay, and point B is fixed at the surface of the big sphere. Okay. And we are going to assume, or we are going to solve it by using the principle of superposition. Okay. And for that we considered that the small cavity of radius A by 2 is having charge density minus rho. Okay. And so we already know that the field of a uniform charge sphere inside the sphere, that formula we already know. So you can say that electric field of a uniformly charged sphere and so we can write it inside the sphere. Inside the sphere, let us call this as our electric field E, that will be equal to charge density 3 epsilon naught, and this is our R vector, and outside we can write this as our electric field is equal to 1 upon 4 pi epsilon naught Q upon R square. Now let us find out the electric field at A. Field at A, and this point A, okay, let me draw it here. So this is a big sphere and this is the cavity, and we are having point A, and this point A is nothing also our center of the big sphere, and this is center of our small sphere, that is a O prime. Therefore we can say that the distance between A and O will be equal to 0. So you can say that our distance from big sphere center, which is our OA, and this O and A are coinciding, so this will be equal to 0. And from cavity center, which is our O prime A, that will be equal to A by 2. Now let's find out the field due to big sphere at A. You can say that field due to big sphere at point A, and that will be equal to E big, and whose value will be equal to 0. And now we find out the because of the cavity, that is negative sphere at A. You can say the field due to negative sphere at A, and let us call this as our E small. Then this E small will be equal to our rho 3 pi epsilon naught, and R is our distance, that is our A by 2. So this comes as our rho A 6 epsilon naught. And with respect to the direction, we can say that the field of a negative sphere points towards its center. So we can say our direction, okay, and that direction will be from A towards O prime. Therefore, we can say that the total field at A final field at A, let us call this as EA, and that will be equal to field due to big sphere is equal to 0, and field due to small is our rho A 6 epsilon naught. So that is our algebraic sum or superposition. So this comes rho A 6 epsilon naught, and direction is towards the cavity center, okay, towards our O prime. Now let's find out the field at B. Field at point B. So this is our big sphere, and a smaller sphere whose center is our O, cavity has been O prime, and this is our B. And we know that this distance is our A, and this distance is our A by 2. So the total distance will be equal to 3A by 2. So first of all, let's find out our distances. And distances from big sphere center big sphere center, which is nothing but our OB, which is equal to our A. and from cavity center which will be equal to O prime B, and that is equal to A plus A by 2, giving us 3A by 2. Now the field due to big sphere at B. Field due to big sphere at B, and for big sphere this point is on the surface, so we can say this our big sphere will be equal to rho A and 3 epsilon naught. Okay. And it will be, direction will be radially outward. Radially outward. Now let's find out the field due to negative sphere at B. Field due to negative sphere at B, and for that we can easily find out the charge on the cavity. So we can say that our charge on the cavity sphere, let us call this as a q prime, and this q prime is equal to minus charge density, and this is 4 by 3 pi r cube, and radius is our A by 2, this whole cube. Therefore we can write that the electric field, because of the small, will be equal to 1 upon 4 pi epsilon naught, and we have this as q prime and 3A by 2 whole square. And if you substitute our q prime and everything, it will be coming as rho times A and 54 epsilon naught, and its direction will be towards O prime. Direction will be towards O prime. Okay. Therefore we can draw, so this is our point B, and because of our big, it will be outward, because B, this big is having a positive charge, and this will be because of our small, because that is negative. So both are in opposite direction. Therefore we can write that our electric field, net electric field at B, will be equal to our big electric field minus small electric field, which will be coming as 17 upon 54 rho A and epsilon naught. And another version of this question can be also modified version. You can try it out. If the point A is at here, at the point of tangency, suppose the point is here, point B is fixed, only the position of point A changes. So that will be another interesting question, that you are supposed to find out the electric field at point A as well as point B. Point B is at the same position, so it is not going to change that much, but the only difference will be because of the point A. Because point A is now at the point of tangency. So you can try it out, the different version of this. Okay. So let me put it through here. You can say point A is at tangency point. So for that we are going to find out the electric field at A and electric field at B. Okay. I can also draw the figure for that. Rest everything is same. Only thing is that this is now point A. Point B is as it is. So this is our O and this center is our O prime. So we are supposed to find out what will be the value of electric field at A as well as at B. And it will be similarly minus, this will be plus and this will be minus. Everything will be same, only we have modified the position of point A. So this is another interesting version of this particular question. You can try it out. Okay. So this completes all the 4 questions for today's. Thank you.